Hello. Today, as part of EECS 435 final project, I would be discussing deep learning applications in remote sensing area. So I'll walk you through datasets and acquisition, deep learning methodologies, some of the bottlenecks and possible solutions, and finally two of them which I tried, the results and the future directions. So the datasets in remote sensing area are not as openly available like text or images or voice. And also the ones which are openly available have a very tedious procedure to be followed like this one, or sometimes you might not even get a matching data for your selected area, and the ones that you get are usually not high resolution. Also, good data is expensive, um, and it requires a lot of storage because of it being very size heavy, and finally sometimes confidentiality agreements with the government. So data augmentation and some other techniques are there to overcome these problems, which I'll be discussing about later on. But meanwhile, applications like land management and military and demographic analysis, all of these have been exploding, and deep learning has facilitated them with really nice methods for accelerating the speed and results. CNN are used for land and water classification. Various RNNs are used for change detection or time series analysis in some land area, crop area, and GANs are used for generating data, for image segmentation, etc. So all of these have started to come up, but still not at the pace required because of the data problems as mentioned earlier. So, some of the major bottlenecks faced by remote sensing applications are data. Data storage is a big problem because all the files and images are so size heavy that usually cloud space is required, and similarly, like scalably for computation, since deep learning methods usually require a lot of matrix calculation, cloud space for the same is also required. And finally, because some of the researchers try to go for simpler models because of these problems, they end up using logistic regression or basic statistical models. So, what are the possible workaround ways for that? For data, we could try data augmentation and synthetic data generation using different methods, which would result in paying less and acquiring less number of data, but being able to train on a deep network instead of compromising for a simpler one. For saving the computation resources, transfer learning is a very nice way, just like ImageNet, training data for once on a really large data set, and then using it for smaller tasks by other people would be really great. And finally, using ensemble learning or attribute compression to be able to use larger and more complex networks is a possible solution. So I tried using data augmentation and ensemble learning on UAV image dataset collected by Zoe for doing road extraction. So this is the image, and next to it are images which are rotated and cropped and have changed colors. So the data set originally consisted of 189 images, but now it's double of that. And also added with ensemble learning, it gave better results. So ensemble learning is essentially giving the input to two or more different models. Here, FCN32, cycle GAN, and conditional GAN, that is pix to pix. And finally, collecting the individual outputs for all of these models. Next, we pass these outputs to a majority voting based classifier composer, that is the ensemble, and which would consider votes from the classifier inputs to and like it will take the maximum and give the final output. So essentially, the best part of all the networks are taken, and the final image is obtained. So the results look somewhat like this, which are way better than individually pix to pix or cycle GAN or conditional GAN. So what I observed is that without data augmentation, I got 84.62% result, but with augmentation, it was a little lesser. But if I would remove these two images from the test set, which are not clearly like a road network, but they have something else in their concrete, um, in their concrete areas, and these are the gray areas. If I remove those two, then the accuracy shoots up to 88.39, which does not happen for the data without augmentation. Hence, what I could conclude is that if the images are nicely represented, equally represented in the training set, and then they are augmented, then it would increase the results for application. But images like these, which are lesser in number, if augmentation occurs, then the overall percentage decreases, and hence worse results. So finally, other things that I could have done is try different GANs and CNNs apart from these three. Percentage of data augmentation techniques, I divided the number of images equally for cropping, rotating, lateral shifting, hue changing. I could have tried a different mix of them. And finally, instead of equal voting by all the classifiers, I could have weighted those models, or increase the number of models altogether from 3 to 5, let's say, and so the accuracy might have increased. So data augmentation and ensemble learning overall proved to be proved to give better results than what it was originally giving, and so these techniques can also be applied to other applications like time series analysis or things like that. Thank you.